Hello everybody, thanks for joining. I'm going to talk about next level quality insurance at Porsche. My name is Marcel Heckner, I'm a sales director at MHP. I'm going to take the sales part, and the technical presentation going to take my colleague Jochen. For those who don't know MHP, we are a consulting company, 5,000 employees focusing on a digital transformation, a 100% daughter company of Porsche, and we are sponsoring the after-show party today. So the good news is we are sponsoring the after-show party after this speech, and the bad news is after the speech. So thanks for joining. AI at Porsche is already in use, so we have several use cases we're already tackling in the industry with at Porsche specifically. For example, we are using AI technology in the area of predictive maintenance. So with this technology, we can predict unplanned downtime in production. Another part is intelligent logistics. That means that we are connecting every HGV with our software, and based on AI, we can define the most efficient way how to work with the intralogistics. Next part is end-of-line testing. For example, we are using AI technology today to connect test bench at the end, and we are measuring electronic motors to prevent failures in this area. So Porsche is a technical leader in the automotive industry, but it takes a lot of effort to build those use cases and also to scale them in a factory or also globally. So currently in Germany, only 13% of companies using AI technology, and most of them not in production. So the question is, how is this way? And how can we as a company, as MHP, take this technology to other companies that they can benefit from this technology and get a positive outcome from AI use cases? And the answer is, how we can do this, is industrial cloud solution. Beside our core business, Porsche and MHP created industrial cloud solutions. Here we take the use cases out of OEMs, put the use cases into products and scale them internal and external. So it's built in production, developed and built in production, and is technology from the industry for the industry. Currently we have several different products in this portfolio. We have logistic products like, as I mentioned, Fleet Executor, our solution to connect HGVs, and together with AI we can find the most efficient way for the interlogistics. Then we have shop floor management. For example, here we have Shifted. It's a workforce planning that help to get the most efficient way for the workforces. And last but not least, we have production. And we're going to focus a little bit more on production today, because we have a whole production cluster. At the bottom, you see shop floor machines and also systems. We have a solution called Integrated to connect to all machines and to auto systems on the shop floor, and to build a data model that then generates the data and send it into third-party systems, but also in our AI solution. So we have here an AI application suite with different products we are offering as a SaaS product to our customers. And the first one I would like to show you is Sounds. Sounds is AI quality insurance. So here we can predict NEOs in the production, inline or end of line, or also in the development. The next one is Painted. Painted is a solution for paint shops. So here we can optimize paint shop performance, and yeah, it's also working with AI. And the product we'd like to give you a deep dive today is Bolded. It's our newest product, and here I would like to introduce you to Dr. Jochen Mahl, who's going to take over and show you Bolded.
Thank you, Marcel. So really glad to be here and to give the introduction of Bolted, our newest product that we actually also took the chance of the Hanover Fair to officially launch this product. So Bolted, I'm talking about this piece right here. As you can see, it's a bolt. It's really not a sexy part. It's only a couple of cents that a bolt or something costs like that. But the impact of that is really huge. So how huge is this impact? I want to ask you guys, what do you think, how many of these parts, how many of these bolts are typically in a car? So raise your hands if you think it's 500. 500 bolts per car, no takers. So let's say 2,000 bolts per car. Okay, some parts. Let's say between 4,000 and 6,000 bolts per car. Any takers? 100,000 bolts per car. Any takers? Okay. So roughly we say, depending on what type of car it is, it's between 4,000 and 6,000 bolts per car. So let's put an even number, 5,000. How many of those 5,000 bolts per car are relevant for safety or functionality? 100%, any takers? 1. 50%, any takers? 30%? 5%? Oh, you're really courageous. Now, so typically it's between 40 or 30%, so let's take an even number, 30%. So that means with these little parts that we have right here, the impact in automotive production is really huge. And as my statement up here says, today's data is not used intelligently. Why do I say that? Because those bolts are safety relevant, we have to document all the processes that are behind that. We have to document the results, we have to have all that data stored in some kind of database. So there's so much data in there which is accessible, but we are not using it. And this is, from my point of view, that's not intelligent. So the worst case scenario for every manufacturer is, in this case, we have some kind of recall action. So we have a problem with our production and we have to recall all our products because we are obligated to be sure that the quality is ensured. And this is like the worst case scenario that could happen. And therefore, but the problem is the data already was there, so why are we not looking at it intelligently and why are we not able to see that beforehand? And this was really the motivation that got us going in developing Bolted. And just that you get a feel for what Bolted really is. So Bolted, from our point of view, is something that where people can benefit who are directly on the shop floor. But at the same time, we have to look at different planning processes. It's really important to see where the quality will go with all our production. But at the same time, the top management of a plant also needs to know how good are all our processes, how good is the quality that we put out of our, or that we put into our products. So therefore, Bolted is a multi-dimensional product from our point of view. But I will tell you a little bit more about that in a couple of minutes. So I already showed you this little piece that is only cost a couple of cents. But what are the real big major challenges that we still have? So on the one hand, our products, and I'm just looking at cars in this case, they're getting more complex and more variety comes into play. So we have a Porsche that we're looking at, and you can have the Porsche in any kind of design package and so on, and the different design packages have different kind of cables that need to be connected, and the cables need to be grounded in the body and so on. So therefore, there are so many different variants that you have. And so this is the one thing, that the increasing complexity with the increasing varieties that we have in our products. At the same time, a lot of workers who are really experienced are kind of running out of their working age. So therefore, we have a decreasing number of experts who have seen everything in production, and who really are essential to keeping the quality going. And this is a conflict that we kind of really need to face. So therefore, the third thing that is really hindering us sometimes in producing continuously high quality is the lack of systematic knowledge management. So we have some kind of quality issue, and we solve this quality issue, and then a couple of months later, a similar quality issue arises, and if we talk to the experts, they say, well, we had this issue there, and then we had the same issue there, and we had another issue which was pretty similar here, and we had to solve all this all over and over again. And we did not really learn something from that systematically. Because on the other hand, we are not able to have this thought or this solution process put into kind of parameters that are applicable to other solutions or to other problems. So this is something where we really kind of focus on how can we make a solution, how can we build a solution that is applicable to different other processes or different other problems. And I just want to give you a quick example. We see that right here, and also at our booth right here around the corner, we have a demonstrator for that. So just think of maybe the rear seat of your car. This is like right here. This is the rear seat of your car, okay? And to be really sure, you want to attach it to the body. So this right here is the body. And once you put a bolt in it, you kind of push it towards the body. So there's a certain movement, and this movement is some kind of resistance, and resistance is in a bolt, it's torque. So we have this first part, which is actually the moving of the part, and then we have the second peak right here, which is the actual torque that we need to apply to a press to actually apply the force. Okay, this is the process as it should be. Okay? So we need to have two peaks, and then the process is okay from a process control point of view, but also from a physics point of view. Let's just imagine something happens. And maybe a worker, because he's new or something like that, is able to put the bolt in from the other side, or this part is misaligned. So let's just imagine that. The problem would be that the process control, we would also reach our target torque with, let's say, 25 Newton meters. And our control system would then tell us everything is okay because we reached 25 Newton meters. But the problem would be, once you do your braking, your kids probably have an extra kind of amount of adrenaline because the rear seat assembly would do something like that. I personally would not like to drive that car. But the problem is, because our control system right here told us everything is okay, this car might have left the plant and might have ended up at the customer. So the big problem from our point of view is that because existing control systems as of today are only able to classify as okay or not okay, we have a large number of so-called pseudo-okays. So process results that are labeled as okay from our current system, but in reality, there's some kind of anomaly that we don't know of as of today. And let me be sure, not every anomaly necessarily means that a car will break down or something like that. There are different kinds of anomalies that we could detect if we look at it more closely. And especially the last part right here, the analysis that we have to do to find such anomalies is really, really tedious. And sometimes it's really hard because there are no systems in place where we can actually do that automated or something like that, or even assisted. So this was the motivation of us also to really dig deeper into the application of AI methods in this whole field. And what we were able to achieve, or what we really found out, that it's if you use AI methods intelligently, you're able to decrease your reaction times. So let's stick with the example that we have before. We're not able to detect like this, the missing second peak or the missing first peak. But if we are able to detect that on this spot where the actual physical assembly process is happening, then we're able to decrease the reaction time to really set up a better product. At the same time, with all this, we're able to translate this solution process not only to this one use case, but also to other use cases. So because we're using, for example, an autoencoder, we can translate the same methodology to other processes, and therefore we're able to decrease the reaction time in different processes that are not really related to one another. And a third really big aspect is, in this case, also efficiency. Because you're able to decrease your reaction time to find some kind of defects in your process, then of course, at the end of the day, it's a lot of saved money. Because just imagine the one thing, your car is built incorrectly on station 50, but your assembly line is like 150 stations long, and you just kind of realize this mistake at the end of your assembly line, then it's a lot of rework that you have to do to actually change this wrong process. And therefore, of course, it's efficiency. And let me give you also some numbers. We started out with this whole idea at Porsche, therefore this presentation is also called Porsche's way of doing that. In the beginning, it was a project at Porsche where my dear consulting colleagues and me, we started getting the first idea of how to do that really good. And in this case, we also found out that with the right use of AI methods, in this case, we are able to detect 7 times more anomalies in the process that our current control systems are able to detect. But at the same time, let me be clear. Not every anomaly necessarily means that the car will break down. An anomaly could also be something like a chatter in some kind of, or in some section of the screw curve. This chatter would not necessarily mean that we have to change the bolt. This chatter would then maybe mean that we have to change the tool because the tool has some wear or something like that. And this is just something, if you don't know that you're looking for that, you cannot find it. And with AI, we're really able to find a lot more things that can benefit us, where we can decrease the reaction time to some kind of issues and also then have a higher efficiency. And efficiency is key. And especially if you look at rework times, we found out that with our solution, you're able to save up to 70% of the rework time for bolting operations. So if you're able to react to some kind of anomalies quicker, then you also save rework time. And this is something where, from our point of view, it's really, really beneficial for not only the automotive industry, but also other industries who are doing bolting processes as well. But we also found out that with this concept, it's really broad and it's really visionary and so on. But we also have to think of that, how are we able to adapt this concept into already running and already operating shop floors? And this is where we came up with the human in the loop concept. We have, as of today, we already have a lot of existing data which are stored in some kind of databases as of today. But we're not looking at it intelligently. And what are the different methods that we could use to actually find out where are our anomalies? And this is where we say we start out with unsupervised learning. For example, we are using autoencoders. And there we find our first anomalies where we then, for example, just really see, okay, where do we have some things that we, as of today, really don't know of yet that we have an issue? And then, of course, as you know, in every AI use case, we do some retraining, we do the anomaly detection and give some feedback. And I really invite you over to our booth. There you can see that, how we can do that with feedback and retraining and so on. And once we get a clear picture of what is actually happening in our data, we then include the expert knowledge. Because experts are still key, and every customer has his own processes, has his own products, has its own, let's say, typical things that might not necessarily be or that might be an anomaly, but this anomaly might not be bad. And this is something where we then incorporate the expert knowledge in our second step, where we then go into supervised learning and also, again, do some retraining, do some classification, and do the feedback. I just want to give you an example, like the chatter that we have in our screw curve. In the first step, we find out, oh, we have some chatter, and we do some anomaly detection where we then say, okay, something is happening, we have a chatter, I don't know that before, so something is wrong right here. This is the first step. In the second step, we would then say, okay, we found out there's a chatter, and then we include the expert knowledge where the expert tells us, well, this kind of chatter, as we see right here, it means that our tool, our bit, has some wear and we have to change the bit. Or, another example, in the end of our screw curve, we see some kind of decreasing gradient. The first step, we would say, hey, something went wrong, we have a decreasing gradient, that's the first time I've seen that, something is wrong. In the second step, we would then say, hey, a decreasing gradient means that the bolt is actually really kind of dying, and we have to change the bolt right away, because there we include the expert knowledge. And this means if the bolt is dying, we have to change it, because otherwise the car really might break down. And this is just the separation of the first step, unsupervised learning, and the second step, supervised learning. And this is also the concept for us that we said human in the loop, because we also have to give context to what we really find out. So, all of the speakers before me showed different architectures and so on, and therefore, I'm not showing something like that. I just want to actually tell you what the impact with this little thingy here, which only costs some couple of cents, in production might be. And you're really invited to come over to our booth, and I'm happy to talk to you or with you about this whole concept again, because from our point of view, a bolt is just the beginning. The whole mechanics of the process might not be only applied to automotive production, but to other production and other industries as well. And at the same time, the mechanics behind this whole process also might apply to gluing, welding, and other processes. So therefore, AWS is a big part of our solution, because it's technical foundation how to do that. And I'm really inviting you over here. As Marcel already said, MHP is the sponsor of tonight's event. So therefore, the good news is my part is over. You can grab a beer. And I'm really happy to talk with you over there. And thank you very much, and have a great evening.